Yeah, thank you. And
Yes.
very good afternoon to you. Very good afternoon to all of you.
Yes, sir. Sir, you want to check your presentation, sir?
Yeah,
Then I will stop sharing my presentation, sir.
okay. Is it visible?
Yes, sir. We could able to see the presentation, sir.
Okay, thank you.
Yes, sir. Thank you. Sir, we'll wait for some 5 minutes.
Okay.
We'll join, sir. We'll start at 4 o'clock.
Sure.
Sir, we are hearing some sound, sir.
Oh, from my side?
Yes, sir.
Oh. Still getting?
Yes, sir. Not from the computer, sir. Maybe from outside.
No, I'm not getting because I'm using headphone also, right? I'm not getting much sound.
Okay, okay, sir.
Good afternoon, Professor Srinivas. This is Praveen, Third Department Civil Engineering, Andhra University. Are you able to hear me, sir?
Yes. Good afternoon to you.
Yeah. Dr. Shivaparuti, is it going to start now or it's going to take some more time?
Yes, sir. I will start, sir.
Professor Srinivas, yesterday we had, today morning, Professor Govindraju has delivered a lecture, and then yesterday Professor Nagesh has delivered his lecture.
Okay.
So this is the last lecture. Yours is the last lecture for this workshop. Dr. Umamesh also delivered a lecture, I think day before yesterday.
Okay.
So everything is going on well. There is quite a bit of question answer session. Almost half an hour is taken for the question answer session, the end of the lecture. So
Okay.
probably if it can be restrained to 1.5 hours, then half an hour can be left out for the participants to ask some questions.
Okay. Okay.
Thank you, Dr. Srinivas.
Thank you.
So, I'll start the introduction. So, good afternoon to all. Welcome you all for this third day of the online workshop on urban storm water management, which is being organized by the Department of Engineering, Andhra University College of Engineering, Patnam. I welcome you all for this second technical session of the program. Today we have Professor V.V. Srinivas with us. So I would like to introduce him. Dr. V.V. Srinivas is currently working as Professor in Civil Engineering at the Indian Institute of Science, Bangalore. He received BE Civil Engineering degree from Osmania University in the year 1994, MTech from NIT Warangal in the year 1996, and PhD from IIT Madras 2001. He was postdoctoral researcher during the year 2001-2002 and a visiting scholar at Purdue University, USA, in the year 2007. His areas of research include stochastic hydrology, regionalization of watersheds and hydrometric networks, prediction of extreme rainfall, floods, and drought, impact assessment of climate and land use land cover changes on the hydrology of river basins, forecasting flows in the river basins, and urban hydrology. His publication include a book and over 130 articles in journals, conferences, and books. He has supervised 8 PhDs. He is visitor's nominee to IIT Roorkee and also recipient of Young Engineer Award in the year 2006 from Indian National Academy of Engineering. Distinguished Alumni Award from NIT Warangal in the year 2016 and Usmania University in the year 2017. Outstanding reviewer recognition from Journal of Hydrology in the year 2016 and 2018 and ASCE Journal of Hydrologic Engineering 2010. He has been in editorial boards of the Institution of Engineers, India, Series A, Current Science, and Journal of Earth Science, Earth System Science. He is a fellow of AP Academy of Sciences for the year 2017. Now, I take the pleasure of inviting Professor V.V. Srinivas to deliver his lecture on performance assessment of urban stormwater drains.
Thank you. Thank you so much, Dr. Shivarthi.
Yes.
So, formally, good afternoon to all of the attendees of my talk. And I begin with thanking Andhra University for giving me an opportunity to make this presentation. So the title, as it indicates, the urban stormwater drains, how to assess their performance, that is what is going to be the main focus. And as you know, the drains are not they are not individual drains, but we look at network of drains. So eventually my talk will end with focus on the type of procedures that we can possibly look at from network theory point of view. So the overview of my presentation, I begin with a brief introduction on this particular problem, and then some of the procedures that are available for assessing performance of stormwater drains. And as I mentioned, followed by that, I'll be making presentation on a procedure that we have developed very recently, that is in connection with performance assessment of stormwater drain network. And this is of significance, especially when there are economic constraints, because when our government wants to invest some kind of funding for retrofitting of drains, etc., there will be limited funds. So we have to have some mechanism to come up with performance indicators for the stormwater drain networks as such, so that we can try to prioritize them. So that is the focus of the last part of my presentation. Then this I'll be illustrating through a case study on Bangalore city. So the stormwater drains, this is how they appear in different parts of our country. They are not properly maintained. So we have vegetation growth in the drains, and also at number of locations we see that there'll be dumping of all kinds of waste into the stormwater drains. And we also get to see some kind of structures constructed in the stormwater drains which prevent the free movement of water into the lakes, etc. So there also have been some kind of initiatives from government side to clear off those encroachments in the recent times in different parts of our country. So this is the general view that we get of the stormwater drains. In the recent times, one aspect that we note is that the more urban areas are coming up in different parts of our country, and it is the scenario same throughout the globe, and it's a rapid urbanization, and combined with that we have effect of climate change, and also we have the effect of land use land cover change. So this picture, it just indicates some of the results that have been obtained by scientists working in the climatology. What they note is that there is increase in equivalent carbon dioxide concentration and drop in snow cover, sea level rise, all these things have been evident. So as far as the urban climate is concerned, what is noted is there is increase in precipitation. So one question that obviously arises is, have there been such kinds of changes in the past? So as this picture indicates, there's some kind of cyclic behavior, right? In the past, we are looking at 400,000 years back to the current time, and we can see some kind of cyclic changes are evident in the equivalent carbon dioxide concentration. So what we can find is that at present, whatever change is taking place, that is much larger than the type of changes that have been evident historically. So this is the main cause of the concern. So climate change has to necessarily go into the analysis. The other thing is change in land use land cover. As these photographs indicate, see, these are some of the photographs which illustrate the condition in Bangalore. The Brigade Road and the MG Road are two prime locations in Bangalore. So you can see that in the past, that it is the past photograph and the recent one. So there's growth in population density together with change in impervious area. So that is what one can clearly see. Generally, the stormwater drains are designed corresponding to about 5 to 10 years return periods, and many locations, since there's increase in impervious cover and increase in intensity of short duration rainfall, the condition of drains is such that they are not able to accommodate the stormwater, the surge which arises during the extreme storm events. So due to the change in land use land cover, what we note is that the peak value of the flow, the flood magnitude, it generally increases, and the response of the catchment gets quickened, as this red curve corresponds to the urban scenario and the green curve corresponds to pre-urbanization. So you can see that the peak magnitude goes up and the time to peak that gets reduced. It means the response time of the urban catchment is much quicker than response time of the catchment in pre-urban condition. Then if we calculate the area beneath the curve, which gives a quantum of the runoff entering into our storm network, the quantum of runoff is much higher. Beneath the red one, we should get much higher volume of the flow. And if you look at the time base, the time base is much lesser for the red curve. The response has quickened, that's what it indicates. It takes much longer time for water to drain out of the catchment in a pre-urban condition. So our network should be in such a way that this quick response, whatever it receives from the contributing catchment, it has to convey that input to the outlet of the catchment without causing the flooding in the locality. The another issue which has attracted attention is that many lakes, here I'm showing the scenario of many cities, Bangalore, Chennai, Hyderabad, Ahmedabad, Delhi, throughout the country at several locations, there have been lakes. And these lakes, mainly they try to detain the floodwaters, holding the floodwaters for some time so that the water can eventually be released. So the lakes, the number of lakes have gone down, and many of the lakes have been encroached, either due to the construction activities or dumping of waste. So that scenario is causing concern. Recent improvement in satellite technology has given us means to verify what changes are taking place in land use land cover. Here on the left side, I'm showing one photograph of the Bangalore taken 1984, and the right side one is correspond 2018. You can see that many of the lakes, these shaded areas are all lakes, and many of them have vanished in the right side picture. So the scenario is same at many locations in the country. So consequently, we are witnessing floods, and they have become common. Very frequently, we are having floods in Mumbai these days, and last year we had floods even in Hyderabad, and throughout the country, so to say. Chennai also we had. And one point which worth noting is that the floods can in general be classified as riverine floods or the fluvial floods, and the urban floods are called pluvial floods, and we have also coastal floods. So some cities like Chennai, which are located near coastal areas, they can be exposed not only to the pluvial floods or urban floods, but also combination of the pluvial floods together with fluvial floods and coastal floods. Of course, the tsunami, etc., can cause the coastal flooding. So when we look into the design of stormwater drain network, so these additional factors are something which are responsible for some kind of uncertainty. If you look at even the rainfall, the spatio-temporal distribution of rainfall, there is quite a bit of uncertainty with that. So what makes the design and performance assessment of these urban stormwater systems a challenge? The main point that I mentioned just now is that it is uncertainty. So one has to account for this uncertainty. There are a variety of procedures, of course. So what is all this about? So when there is uncertainty, there is lack of understanding of the phenomena and the process that are involved. So what are the processes that we are talking about? If there is going to be rainfall, when it is going to rain, and how much is going to be the quantum of rainfall? And not only that, because mainly in our part of the world, we are bothered mainly about rainfall. But in some places where we have even shallower groundwater depths, the issue gets complicated because there is no scope for enough water to infiltrate. So that also causes the increase in the risk of flooding. Now I'm just giving a glimpse of various types of uncertainty that people have looked at in the past. So objective and subjective kind of uncertainty. This is a symbol of classifying. So if we talk about objective uncertainty, it can be something which can be quantified from samples. What are these samples? Whatever data that we get from field are nothing but samples, which are deemed to be drawn from a universal set, because basically the frequency analysis is what we look at in this particular thing. So whatever sample or whatever data that we are getting at, it could be looked at as some kind of a subset which is drawn from a universal set, and those universal sets are represented in the form of some kind of distributions. I'm going to talk about that more in the coming slides. The next is subjective. If what is subjective kind of uncertainty? It is something which cannot be quantified. Now there are something called natural uncertainties. What are these natural uncertainties? As I'm mentioning, if the groundwater has an effect, if the rainfall is going to have an effect, so when it is going to rain, what will be the spatio-temporal change in rainfall? Those could be the natural kind of uncertainties. Likewise, the groundwater change, the groundwater level, how it is going to change if we are encountering shallow groundwater depths. All those things can go into natural uncertainties. We have model uncertainties. So whenever we want to, in the stormwater drain context, let us say we want to develop some kind of models. We want to know how much quantum of water is entering into the stormwater drains. So we develop some kind of models, and those models have uncertainties. So the model, whether it is able to properly represent the underlying mechanism, that is the first question. So if the mechanism is not properly understood, model is developed but is not properly representing the mechanism. Each and every model that we choose has something called as parameters. So for parameter estimation, there are a variety of procedures. So one can have improper understanding of the system, but whatever model is developed, the parameters of that model are estimated in a perfect manner. Means whatever estimates are obtained, they are somewhat reliable. So the issue that arises is, have we properly understood the system in developing the model, and for that whether the parameters are properly estimated. Now if you look at the combination of those, we have type 1 error and type 2 error. What is type 1 error? The model is inadequate in representing the system because proper understanding has not gone into development of the model, but the parameter values are correctly estimated. This is type 1 error. And the type 2 error is one has obtained a proper understanding of the system, and after understanding the system, whatever model is developed, that is good, but the uncertainty is associated with that model. It has to quantify in terms of parameters. Those parameters are not properly estimated. So it is type 2 error. There are different procedures for estimation of parameters. So in the following slides, I'm going to touch upon that aspect. Now, next thing is data uncertainty and operational uncertainties. Now, operational uncertainties, basically these stormwater drains have to be constructed and they have to be properly maintained. So what is the type of material that is going to the construction, or are they properly maintained, and what are the other human factors which are going into that? All those things go to operational uncertainties. Now, data related uncertainty is one of the biggest uncertainties that we deal with when we are trying to model the flow into stormwater drains. The main thing is as we look at the precipitation records, the precipitation records are often inadequate, and there are hardly a few gauges in whichever area we are looking at. A situation may arise where we may not have even a single gauge. We have to come up with. I was also part of the Amaravati city, AP Capital Development. I was involved in several committees there. So there was no proper gauge at that particular location. So sparse density of gauges is an issue. We may have gauges which are far off, but strictly speaking, if you have to have proper idea about how the rainfall changes in a particular area, we have to have the rain gauges located at appropriate locations. Now, gauges could be there, but the type of gauge which is there at a location may have some kind of limitations. So limitations, the grading procedure is also an issue. By default, we have many rain gauges for providing us rainfall observations. The radar technology is finding its way. It is already being used, but it needs lot more development within our country. If radar rainfall is developed, it gives a clear indication regarding the rain drop size distribution and how it is spatially varying in the surrounding areas. It can cover a very large area. But if you have rain gauge, it may not. It may provide information at a particular location. Also, one more issue is that usually rain gauges are not of automatic type. So we take readings once in a day, etc. So all these have implications in whatever analysis we are going to perform for the stormwater drain. Now, short and limited records is another issue. The gauge may be there at that location, but the record may be available for a limited time. So we have to have proper understanding of rainfall. For that, reasonable amount of rainfall is necessary. And then discontinuity is another issue. The available records, even if they are short, they may have some discontinuities. So discontinuities should not be there, and we also have to have information at adequate number of locations in order to provide complete understanding of the spatio-temporal distribution of the rainfall. Now, inconsistencies, non-homogeneities, etc. Some gauge may be non-functional during certain time it may have been shifted from one location to another location. So all these, the associated non-homogeneity inconsistencies are one more issue which need to be addressed. And then we have data handling and transcription errors. So there are various things that one need to look into. So these radars, as I mentioned, the IMD is setting up radars, and hopefully once we have data available from radars, we'll be in a better position to get a clear understanding of spatio-temporal distribution of rainfall. Whatever said and done, if we are looking at forecast, that's a different type of problem, and this long-term simulation is something which is different. If you're trying to design stormwater drains, it is not the radar may give rainfall over the last, since last 1 year, the radar has been set up, it may be giving us information. That information may not be adequate. If you are looking at long-term planning of a stormwater drain network, or if we want to assess the performance of an existing stormwater drain network, we have to have very long records. So what I want to emphasize is that radars may come up, and whatever information they provide will be useful for forecasting, but still for long-term prediction or performance assessment of stormwater drain networks, we need something more. We need longer records, and therefore have to consider some procedures which can help us in that particular direction. Now, the performance of a stormwater drain, let us say the drain is existing. There are some terminologies that one should have clarity before we get started. So this is what I'm defining here. There is a drain, and discharge is entering into a drain. That discharge, I'm calling it as a load. So that load is represented by term QD. And the capacity of stormwater drain, I'm representing it by QC. It is also called as resistance in different literatures. So when do we say a stormwater drain is performing its task satisfactorily? If its capacity is adequate to contain the discharge which is entering into a stormwater drain, then we deem that it is in a proper situation. It is able to handle whatever discharge is coming. So it will prevent the flooding situation. That is what is expected. So the QD, that is discharge entering into stormwater drain, if it exceeds the capacity of stormwater drain, then the stormwater drain is in a failure condition. Now, if you look at these two, capacity of the stormwater drain and discharge entering into stormwater drain, what are they dependent on? The capacity of a stormwater drain, if you look at, G is a function. It is a function of several random variables. There are m1 number of random variables. The discharge entering into a stormwater drain is represented by another function of another set of random variables. There are m2 number of random variables. So m1 random variables are influencing the capacity of a stormwater drain, and there are m2 random variables which are influencing the discharge which is entering into a stormwater drain. What can be the typical examples of this? The capacity of a drain when we are calculating is one simple formula, is the Manning's formula that we use. So it takes into account the channel dimensions, like width, depth, slope of that, the roughness of that, etc. So all these are random variables influencing the drain characteristics. Now, if we look at the QD, QD, so QD is a function of m2 number of random variables. What is QD? It is a discharge which is entering. What does it depend on? It depends on the characteristics of watershed. So what is the shape of watershed? What is the slope of watershed? What type of soils are there in the watershed? What is the type of land use land cover in that? And what is the type of rainfall that that watershed is receiving? So all these influence the discharge which is entering into a stormwater drain. So now the failure is a situation where the discharge is exceeding the capacity. So this there are several formulas, Chase's, Manning's, etc. So here I'm mainly focusing on Manning's. So the Manning's formula, if you look at, so we have R, which is the hydraulic radius, wetted area by wetted perimeter, and we have the friction slope, which is put in here, friction head loss due to friction per unit length of the channel or drain. So this is the pressure head plus velocity head plus data head the upstream side and downstream side, both we are balancing, and this HF is head loss due to friction. Bernoulli's equation is what I'm showing here, and the friction slope is head loss per unit length, so which is sine of this angle theta, and same angle we have here, sine of angle theta. So we have this difference, so Z1 minus Z2 by length, that's what we have. So one can approximate the sine of theta with tan of theta for small angles of theta, and based on that we can approximate the friction slope with bed slope. That's what we do in the analysis. The other point is the Manning's equation dimensionally homogeneous or not? That's the other question. So if you look at the dimensions of this, we have the discharge on left hand side. So the discharge has a unit of LQ by T. That is the dimension of that. And right side, if you see, A is N is Manning's roughness coefficient. These are the typical values. It doesn't have any dimension. And we have R, which is hydraulic radius, which is weighted area by weighted perimeter. It's also called as hydraulic mean depth. And we have the bed slope. Bed slope also has no dimension. So now if we look at the homogeneity, the equation is dimensionally homogeneous. There's a hidden dimension of L power 1 by 3 by T. So if we substitute this, if you want to convert the SI system unit, the units of that from SI to foot-pound system, then we can replace this with this 3.281 feet as 1 meter. So we get this particular formula. So the point that one should note is usually we encounter several instances where the equation is deemed to be non-homogeneous. The point I want to emphasize is the equation is homogeneous. That's the point to be noted. Well, there's a different formula in equations in the fluid mechanics, which we can use to calculate the areas, perimeter, etc. And basically substituting that in this expression for the discharge through a stormwater drain, we can get the equation for different shapes: rectangular shape, the trapezoidal shape, circular shape, etc. Now, the failure occurs when the discharge entering into a stormwater drain exceeds the capacity of the drain. Now, the capacity of the drain we have seen that one of the ways to calculate that is by using Manning's formula. Now, the discharge entering into a stormwater drain, how to determine that? Before going to that, let us say I question the use of this formula itself. We are getting some estimate of the capacity of a stormwater drain using Manning's formula. Now, the thing is it representing true capacity? Why am I raising that particular question? We have seen this photograph right at the beginning of my talk. There is a growth of vegetation, and there is lot of waste material is dumped into stormwater drains, etc. So, can we use the Manning's formula to come up with the capacity of stormwater drains? So it is obviously, it will not give a correct indication of the capacity of that because they are not properly maintained. If the drains are properly maintained, then we can rely on that particular formula. But we know very well that our stormwater drains at many locations, they are in this kind of situation. Now, how to address that? So there is uncertainty even with the capacity. Whatever capacity I'm representing by Manning's formula, that capacity itself, we can represent it with a probability density function to address this uncertainty. So what is this probability density function? We can consider that the shape of this probability density function is either of normal type, log normal type, etc. A lot of assumptions can be made. Again, this is an issue. There is no unique distribution that can represent all situations, right? So now, since I mentioned that the capacity of a stormwater drain is not fixed, but there is some uncertainty with that, and we can represent it by probability density function. I talk about this probability density function. So what is probability density function? Let us say this is a random variable x, continuous random variable. We are having several values, of course. So these x values, x1 to xn, are like basically the capacity of the stormwater drain. Capacity of stormwater drain is not fixed, it is changing. Why it is changing? Because the dimensions of channel are changing. due to the material which is getting into that. We also have some kind of sediment, etc., moving at the bottom. So that can also change. So it is dynamically changing. And the capacity, let us say somebody has noted all those aspects and they have come up with the estimates of the capacity of the drain at any given location. So we can, for that random variable, we can write probability density function. And what is that actually indicating? This Ni, we can divide this whole range of the random variable into several class intervals, each of size delta x. And what exactly are we doing? There are n number of data points. And once I divide this whole range into number of bins, each bin may, let's say I'm looking at ith bin, it has ni number of data points. So ni by n, what does it give me? Ni gives me frequency of data falling in ith bin. Ni by n gives me relative frequency of data falling in ith bin. So this I'm dividing by class interval size delta x. And the limit of this, as the class interval size tends to very small value, delta x tends to 0 means class interval size tends to very small value, and as the number of data points that we have tend to a very large value, means we are having a very large data set, the n tends to infinity, then that limit is what is the probability density function. So this we are visualizing it by a nice symmetric bell-shaped function in the case of Gaussian distribution. And with different distributions, we have the skewed nature, etc., coming in. No, normal, log normal, etc. Now, this slice that we pick up here, this slice, what does it give us? The area of this particular slice, it gives us probability of the random variable value falling between A and B. This slice is cutting horizontal axis at A and B. So if we are talking this in the context of the capacity of a stormwater drain, that capacity of stormwater drain falling between A and B, that probability is what this particular shaded area provides. Now, the whole area below that is 1. So this capacity of stormwater drain is expressed by Manning's formula. And the discharge entering into stormwater drain, there is one more thing that we need, because failure, I said, it occurs when discharge is exceeding the capacity of a drain. Because the excess discharge, it will flow and it causes flooding. Now, how to determine this discharge entering into a stormwater drain? So we need a stormwater model, and we also need design rainfall. Stormwater model, it gives us for any unit of rainfall which is given as input to urban catchment, what is the response of that particular catchment? That is what the stormwater model it can simulate. And next thing is, historically there have been any location. Historically we have several rainfall events, but whatever rainfall event we are going to get in future, that will never resemble any of the historical ones. So future we are likely to get several different types of storm events of different durations. So they will not exactly resemble. So how to come up with a design rainfall? So design rainfall is what for the stormwater model, I like to provide rainfall, synthetic rainfall hydrograph. The synthetic rainfall event I would like to provide as input. The synthetic rainfall event is designed in such a way that for any chosen interval, for example, 5-minute I pick up, or 10-minute I pick up, or 15-minute I pick up, for any chosen interval of time, it should give the maximum possible rainfall, because with that kind of event, I can assess the performance of an existing stormwater drain, or when we are taking up studies even to plan a stormwater drain, that is the type of hydrograph I'll be looking at. Of course, we can even provide historical events as input to that to see what kind of result we get, but to evaluate whatever network we are looking at, we need this design rainfall. So where do we get what can be picked up as stormwater model, and how to prepare a design rainfall? Those are the questions that we encounter in this type of analysis. Stormwater models are not unique. This is a big list I have put here. So several models are being used, and of course in our country, the micurban and different variations of the versions of the stormwater management model people are using. So not only this, as you can see, there are several models which are there. So each type of model that we pick up, it has implications on what result we get from this analysis. So we have uncertainty in choice of the stormwater model. This is something which needs to be addressed. So rather than relying on one model, it is better if you try at least a couple of models to see what difference we get in the results from the analysis. Now, along with the stormwater model, other point I mentioned is design rainfall, synthetic rainfall that we want to get. Now, for a given rainfall, can flow in stormwater drains change? Means, let us say you have chosen one stormwater model. There's the option to pick up several stormwater models, but let us say you picked up one stormwater model and keeping the stormwater model as fixed. And if we are providing a rainfall as input to that particular model, are we likely to get same output from that all the time? I run the model 10 times. Am I going to get same output from that model or not? That's the question I'm posing. No, the question, the values will be different. Why? There is uncertainty associated with the urban catchment. What can be the uncertainties? There can be difference in antecedent moisture condition. There are impervious areas, there are pervious areas. So when we are talking about pervious areas, their antecedent moisture condition will definitely affect the response of the urban catchment. And if you are talking about other aspects, there can be lakes in the urban catchment. And these days we are emphasizing more on rainwater harvesting. So the rainwater, it can get retained or it can also get detained. The detained water is that which will eventually find its way into stormwater networks. But what is retained storage? It is something which is captured and eventually it gets lost in the form of evapotranspiration, right? Evapotranspiration, that is the process by which it leaves the catchment. Now, because of, and of course, it also depends on how deep is the groundwater, etc. So there are several factors which play a role. For a given amount of rainfall, response of urban catchment will not be the same all the time. So that's the point that I wanted to take note of. Now, how do we construct the design rainfall? I said it is synthetic one. Historical ones you can pick up, but for the design analysis or performance assessment of existing networks, we consider something called as design rainfall. So how do we construct this design rainfall? There are several procedures for this also. Alternate block method, half curve method, Chicago design storm, there instantaneous intensity method, different methods are there. So if somebody is making an attempt, once they perform this analysis, there can be difference in the type of model being considered. Even if the type of model being considered is the same, the way how they are constructing the design rainfall could be different, right? So there are several type of design hydrographs that people have developed in various parts of the world. So this has uncertainty. Now let us look at when we are talking, because we are discussing about extreme rainfall. Synthetic extreme rainfall is what I talked about. What is the magnitude of rainfall, extreme rainfall received in different parts of our country? Investigation carried out by Deshpande et al. This is way back in 2012. They have, of course, the records are well before that. That's what they collected. Now these values might have gone up because more severe events have been witnessed in different parts of our country. Just a few seconds. So this is 1 hour duration rainfall, 3 hour duration rainfall, 6 hour duration rainfall, 12 hour duration rainfall. So if you look at within 1 hour, how much rainfall is received, there have been instances where about 13.5 centimeter rainfall is recorded in 1 hour. Right? Oka, that is the location which they have mentioned. There are several cities. I have highlighted them with these boxes, red color boxes. In about 3 hour duration, the Hyderabad has received around 24 centimeters. So recently also we had extreme event there. So large quantum of rainfall is delivered within a short duration of time, and that is what creates a major problem. Now, how to construct? We are discussing in the context of synthetic rainfall or the storm event construction. And the procedure I'm discussing is alternate block method. So we have intensity, duration, frequency relationships. So this is one typical example I'm showing, but similar curves we construct even in India. So basically, the synthetic storm corresponds to a particular return period. For example, corresponding to say 100-year return period I want to construct, so I can pick up a value here. So horizontal axis, what we have, intensity, duration, frequency plot, it is a duration. Vertical axis has rainfall intensity. Now, corresponding to each and every point on horizontal axis, which is correspond different duration, I erect a vertical line onto the curve that I'm looking at. What is this curve? Each curve corresponds to different return period. The return period is indicated here. 100-year return period, 50-year return period, 25-year return period, 10 and 5-year return period. So 5-year, 2-year return period, if we want to get, we can erect a vertical onto this curve and get the corresponding point on the vertical axis. So the unit of this point on vertical axis, because rainfall intensity, we have centimeter per hour or inch per hour like that. So it is L/T dimension. Horizontal axis, we have time dimension. So if we take product of these two, we are going to get the depth of rainfall. L/T on vertical axis and T on horizontal axis. The product will give us L dimension. That's the depth of rainfall. That's what we are going to get. So when we are constructing a synthetic rainfall hydrograph, we have to pick one of these curves, and each curve corresponds to a return period. So we want to construct synthetic hydrograph corresponding to a particular return period. So for several points picked on that particular curve, if we take product of the horizontal axis value and vertical axis value, because one has dimension of L/T, another has a dimension of T, we are going to get depth unit. So once we get the depth unit, then we can work out and then come up with those the synthetic hydrograph. I'm going to talk about in the coming slide, but there is one more issue which crops up. What is that? Let us say I want to know what is the urban flood corresponding to 100-year return period. Usually in the beginning slides, I have mentioned that return periods like 5 years, 10 years, 2 years are what are being looked at when we are trying to design urban storm drains. So if I want to know what is 5-year return period urban flood, what is the corresponding rainfall I need to pick up? That question will arise. Will a 5-year return period rainfall correspond to a 5-year flood? No. Mostly, say we got opportunities to see several reports being prepared by government organizations, where what we see is that they make an assumption. 5-year return, 10-year return period flood will result in 10-year return period. 10-year return period rainfall will result in 10-year return period flood. Even in riverine floods, 50-year rainfall will result in 50-year flood. 100-year return period rainfall, for example, design of a dam, 100-year return period rainfall will result in 100-year return period flood. That is the assumption which I have come across several studies. But one point that you can take note of is the return period of rainfall, return period of flood will not be exactly the same. And these figures, what I'm showing here, they are extracted from a set of books which are brought out by Institute of Hydrology, Wallingford, United Kingdom. And what we can see is on horizontal axis, we have a return period of storm, is return period of rainfall. Vertical axis, we have return period of flood. So if we erect a vertical, for example, I pick up the 10-year, let us say 10-year rainfall I pick up, and corresponding to that, I get a point onto the vertical axis. You can see that is less than 10 years. So any return period rainfall is resulting in the corresponding return period for the flood is less. So given return period rainfall will result in a flood whose return period is lesser than that. So that is what we can get it. So this is in excess of 30 years and below 30 years they have given. Anything you pick up, that's what we get. Basically this, if you see, for example, this we pick up, this is 25-year return period rainfall will result in 15-year return period flood. This is what it indicates. So there is depth of studies. So the point to be noted is, are we having these kind of curves for use in our country? People are interested in doing this kind of research, but the point is data which are necessary for getting that kind of result are unavailable. Why? Because we have the constraints. We have constraints in getting rainfall data, station data. We also have constraint in getting unregulated flows. If some structure is there, let us say somebody is operating and that data we have to use. We cannot come up with this kind of relationships. So this kind of relationships, if somebody can develop for our country, that will be very, very helpful. In different urban areas, the response could be different. So one has to come up with a relationship which can help us to say that this much return period of rainfall will yield this much return period flood. So this kind of relationships will be very useful. Now we are discussing about construction of synthetic hydrograph because that is the basis to come up with estimate of flows into the stormwater drains. Now, as I said, if I'm interested in, let us say, 2-year return period synthetic hydrograph or a storm, I have to pick up this 2-year curve and several points on this I can choose, and I can determine what is each and every point's corresponding x-axis value, what is corresponding y-axis value. I can take product of both, and that will give me depth, because vertical axis is in L/T dimension and horizontal axis is in time dimension. If you take product, we'll get the depth units. So now once we get the depth units, what is that we are going to do? We have to take difference between the consecutive depths. So for several points we are going to get depths, so we have to take difference between the consecutive points to work out what is the additional quantum of rainfall which is received for every additional duration. For example, 20-minute duration, if I pick up, I get this particular point, corresponding y-axis value I get something, so that product will give me something, and the product for this 25 will give me something. So I can take difference between two consecutive values. So within that additional 5 minutes, what is the additional quantum of rainfall which is received, that information I'll get. So that will be the basis for construction of the synthetic hydrograph. Now there is one more question. What is that? Here we are seeing the intensity, duration, frequency plots. So when I talk about return period, frequency, etc., there is some frequency distribution which is going in for construction of these curves. So what should be the frequency distribution that we consider to construct these particular curves? There are several distributions. So this particular slide is showing several distributions that are in use in hydrology, and usually it is generally extreme value distribution which will be fitted, and if you're looking at partial duration series, it is generalized Pareto distribution which will be fitted. Excuse me. And not only this, many distributions are coming up in our literature. Halfen distribution is one such family. And after we choose distribution, as I said, general extreme value distribution is chosen by default. Or people who are interested in applying 2-parameter distribution, they apply extreme value type 1 distribution. Now, having chosen the distribution, next the point which comes up is distribution has something called as parameters. We have location parameter, scale parameter, shape parameter. If we have 2-parameter distributions, we have location and scale parameters. If we have 3-parameter distributions, we have location, scale, and shape parameters. If we have 4-parameter distributions, then location, scale, there can more than one shape parameter. Now the issue is how to come up with estimates of those parameters. For that, we have several methods which are available, and I have highlighted some of the common methods that researchers are considering in the area. L moments is widely used these days, and the conventional it is method of moments and method of maximum likelihood which are considered. And once we get these curves, so after fitting the distribution, after estimating those parameters by choosing one of those procedures, we come up with these curves. So the point I would like to emphasize is that there is uncertainty in these curves. What is that uncertainty? Which distribution is chosen? Which method is considered for parameter estimation? That can result in different set of curves, even if same data is given to different people. So that uncertainty is very well there. Now, having constructed this, next task I was mentioning is we have to take product of the values. What is this? This is horizontal axis value. I said we have to pick up one of the curves, and each and every point chosen on the curve will have x-axis value, y-axis value. So we have to take product of those. So these intensities are all y-axis values, and these durations are x-axis values. Once we take product, this has L/T dimension, this has the t dimension. So we have depth coming. So what is that we have to do next? Take difference between the consecutive values so that we can make out how much additional depth of rainfall is received. So once we do this, after taking these differences, we can make use of this particular information to construct a synthetic hydrograph. How do you do that? The largest value will be put in the center, next largest value here, next largest value here, what is these values? So I'm talking about these values, these delta D1, delta D2, difference between consecutive values. After taking product and then taking difference between consecutive values, whatever we get, those values, these differences are what are plotted in this particular manner in order to create this synthetic hydrograph or synthetic storm event. This synthetic storm event, what is speciality? As I mentioned, any chosen duration. You pick up, for example, this has the smallest unit as 10 minutes. So for 10-minute duration, it gives the largest maximum quantum of rainfall. For 20-minute also, it gives maximum quantum of rainfall. 30-minute also, it gives maximum quantum of rainfall. So compared with all the historically observed events, this is a single event which gives the largest values corresponding to any chosen duration. So this will be provided as input to our stormwater model, urban stormwater model, for example, like stormwater management model. And then the output of the stormwater management model is nothing but flows which enter into the stormwater drains. Now, the next important question is, as I said, I was involved with our Amravati city in several committees. I was there. So the issue is you don't have the gauges at desired locations. So if the ungauged locations are there, then what is the issue? If ungauged locations are there, you have to come up with estimates of rainfall in the absence of information. So how do you do that? We have to go for regional frequency analysis. So regional rainfall frequency analysis is what we can come up with. So what does that particular thing involve? Regionalization is one of the steps where we have to identify locations which have similar characteristics of rainfall. For example, I'm looking at one particular location and there are several other locations. So with respect to this location, which other locations have similar climatic conditions identify, and I try to draw upon information from those locations. They may be nearby, but there could be difference in the elevation. So that is not allowed. So they should located nearby, and the elevation difference should not be significant, and all those factors should be taken into account. And they need not be physically located, geographically contiguous locations. They can even be far off. But if in climatology sense, if one can establish homogeneity, one can try to draw upon information from multiple locations. Okay, there are several procedures which are developed for the regionalization and frequency analysis. What we talked about is fitting generalized extreme value distribution, parameter uncertainty, all those things I talked about. So that we have to do with the information pooled from several similar locations in order to come up with estimates at reliable estimates at those locations which have shorter records or no data available. So we can still come up with the rainfall estimates. So once we do that, next is what we run the stormwater model and we get the flows into the stormwater drains. Now the question is, now that we got flow into stormwater drains, how do we evaluate performance of the stormwater drains? Conventionally, these three indices are widely used. One is reliability, other thing is resilience, and other thing is vulnerability. When I talk about reliability, what is reliability? Probability that a stormwater drain will perform its intended function without entering into a failure mode. So it is able to safely convey the discharge which is entering into it all the time, let us say, then it is 100% reliable. And what is resiliency? We know very well that no system is designed in such a many locations, of course. These systems are designed in such a way that occasionally they get flooded. So when it gets flooded, means it is entering into failure mode. How quickly can it bounce back? If the resilience means within a very short time, it bounces back to normal situation. So that is a measure of resiliency. Then we have vulnerability. And what is vulnerability? It is the consequences of the failure. What is consequences of failure? Let us say a system is getting failed once in a while. Getting failed means getting flooded. We are talking about stormwater drains. Stormwater drain is getting flooded once in a while at a location. But whenever it is getting flooded, the excess water is too much at that location, let us say, it means it is highly vulnerable. So the consequences of that failure also should not be high. And the system should be such that it bounces back to normal conditions in a short time, and most of the time it should not get flooded. So these measures provide us some information about the performance. Now, how to proceed? Now the thing is, we discussed right from beginning that a system is said to be in success condition when the capacity of that particular drain, stormwater drain, is more than the discharge is entering the stormwater drain. I'm defining a performance function by this W, say QC minus QD. What will be the magnitude of this if capacity is more than the discharge which is entering into that? Then the difference is going to be positive. If the capacity is just adequate to contain the discharge which is entering into it, it means that it is in a limit state condition, means W value will be 0. But if capacity is lower than the discharge, then it becomes negative, right? So for W, for system to be in success condition, W should be greater than or equal to 0, basically. Now, why only we are focusing on the quantum of flow in the drain? We can also look at performance in terms of velocity of water movement in a drain. Typically, when we look at flow in a stormwater drain, the velocity would be of the order of about 2 meters per second or so, 2 meters or 2.5, 3 meters. Generally, it will be around that. Now, if the velocity of flow in a stormwater drain is exceeding, let us say it becomes 4 meters, etc. at some location, what is going to happen? We have bed material of the stormwater drain. It cannot withstand with such large velocities. So what is going to happen? Scouring is going to take place. So in terms of velocity, also we can define performance function. This is Vmax minus Va. What is this Vmax? It is the maximum allowable velocity, and Va is the actual velocity. So the actual velocity is lower than maximum allowable velocity, means second term is lower than the first term, then we are going to get a positive value for W. But if the actual velocity of flow in the stormwater drain, which is second term, is more than allowable velocity, this Vmax, then what is going to happen? We are going to get negative value for W. Similar thing holds true in analysis with the minimum velocity. What is minimum velocity? Why are we bothered about minimum velocity? If minimum velocity is adequate, then the water is getting into stormwater drain that can safely convey whatever the material is being dumped into that. Means if nobody is dumping, still some kind of sediment gets into that, and that sediment will be able to get transported by that particular water. But if the minimum velocity, let us say it is dropping below the critical value. What is the critical value here? This is the minimum flow velocity in the conduit or stormwater drain. I'm showing with the first term here, and minimum velocity, that is the threshold which is put, is Vmin. If the first term, which is the velocity of flow in stormwater drain, is dropping below the second term, means minimum velocity which is desirable, if its flow is velocity is dropping below minimum velocity which is desirable, then what is going to happen? First term's magnitude is less than the second term magnitude, so obviously W will become negative. So in all these cases, if W value is negative, it means that system is in failure mode. I mean our stormwater drain is in failure mode. So considering this, one can proceed. So we have line drains, the unlined drains, all sorts of things are there. So scouring and all that, no, we can get to see the natural systems. Now, reliability, when I'm talking about for a stormwater drain, that reliability I can represent with the probability. What is that probability? Probability of the capacity of a stormwater drain being greater than or equal to the capacity being greater than or equal to discharge which is entering the stormwater drain. So this is other way we can write it as the probability that the W, which is my performance function, is greater than or equal to 0. So in this situation, the stormwater drain will be able to safely convey the discharge which is entering into that because of its capacity being greater than or equal to the discharge entering. Now the thing is, how do we come up with the estimate based on this probability density function? Why I'm coming with the probability density function again here? Because The horizontal axis here I'm showing load. What is that? Discharge entering into a stormwater drain. Discharge entering into a stormwater drain is not a single value. It changes over time. So if I'm looking at the different values attained by this random variable, so-called random variable, which is nothing but discharge entering stormwater drain, I get probability density function. Now, if you look at this particular point, probability of the discharge entering into a stormwater drain being greater than its capacity, that's what we are getting. What is that particular area? Discharge being greater than the capacity. So that is given by the risk. So what is that particular factor? This unshaded part is what is the risk. Probability of discharge entering into a stormwater drain being greater than or equal to a particular value on horizontal axis. That is what this is showing, right? So that is what is risk. Now, yeah. So you may recall that I said we have to consider so-called probability density function in order to address uncertainties, because the capacity of stormwater drain is not fixed. So this particular graph, if we carefully see, we have two probability density functions. On left side, I have probability density function for loading. On right side, I have probability density function for capacity. What is this loading? How much flow is entering into stormwater drain? On the right side, what I'm putting is for capacity of a stormwater drain. So can the right side one be left side or left side be right side? Can we shuffle them? We cannot shuffle it because the left side one should be at left side only. Why? Left side one is indicating how much flow is entering into stormwater drain, and right side one is indicating how much is the capacity of a drain to accommodate that. So if the capacity is towards the left and the probability density function of the loading is towards the right, it means the system is not in a good condition. Straight away we can say that. Now, what is that we are talking about? We are talking about the probability density functions of the discharge entering into stormwater drain and capacity of stormwater drain. Now, if you carefully observe these integrals which are being put, what exactly they show here, if you are calculating the risk, this risk, so what is that risk? That is, this one is the load which is entering into stormwater drain, and this is the capacity. If I fix a point, for example, I fix a 0.5 here, right? So if I look at any area towards the right side of that, this FLDL, what it gives me, FLDL will give me the shaded area, integral from 5 to infinity, FLDL will give me shaded area, and that is the probability of the load exceeding the capacity 5, right? The capacity, this point, for the capacity, this is the probability density function, and for that I'm putting a point here, and I'm looking at how much area is there beneath the probability density function of the loading curve to the right side of that. Now, conversely, reliability also I can work out. If left side area I'm picking up, it is the reliability. Now, the thing is, the load, the probability density function of load and probability density function of capacity both have corresponding random variables, and these random variables, if we are considering them to be independent of each other, we in the probability theory we read, right, probability of an event A into probability of event B, if they are independent of each other, the joint probability, how do we get? We obtain by taking products of the two probabilities, probability of A into probability of B. Analogous to that, here the joint product is what we are taking here. The GCDC, whatever is being shown here, that GCDC is nothing but this vertical strip. So what does it give us? Probability of the capacity lying in a small range here surrounding this particular point, which is located on horizontal axis, right? And so the shaded area which is given here into shaded area which is given by the vertical slice shaded area into the gray color shaded area, the product of that is what is here. And the outer integral is for the capacity curve. So outer integral is for capacity curve. Each and every point on that I have to locate on this, and I have to take joint product of these two. Means the vertical slice into shaded part. That kind of thing I have to go on doing, and then I will get the risk. That is a point to be noted. Now the issue, if somebody is willing to criticize, one point one can criticize is why is it nicely Gaussian? So this is assumption which is people are doing the analysis. In reality, nobody is taking measurement of the capacity of a stormwater drain. Why capacity? As I said, it changes, is it not? Capacity here earlier I showed, right? Because the stormwater drains are in this kind of condition. Nobody is monitoring them to see what is the capacity, how it is dynamically changing over time. So one is assuming that it is nicely appearing as a Gaussian shape. Now, what is loading? How much flow is entering into stormwater drains? Nobody is taking measurement of even that. So recently, some initiative made here in Bangalore. So we are trying to take readings. But the issue is long-term records. Many cities don't have, and even if they fortunately have it, the available records on the loading or the flow entry into stormwater drains is very, very limited. So if we have adequate information on these two, then using that we can construct this probability density function to work out this risk and reliability. Because we don't have data, the Gaussian assumption is what is made. Now, as I said, these are the different so the method of direct integration is what we have seen. That requires knowledge of the probability density functions of what all we have on the right hand side of these equations. But unfortunately, we don't have knowledge on that because the records are not being maintained. Now, in the absence of knowledge to construct probability density function of those things on the right hand side, what we do is we go for direct integration procedures. Okay. And the direct integration cannot be done. So we have shortcomings with that. So because of non-availability of information, so we proceed for the numerical integration procedures. So there are different procedures. And first order variance estimation method, Rosenbluth 2-point procedure, Monte Carlo simulation procedure. So I'm going to talk about some of these briefly. So if you look at the reliability index of a stormwater drain, that reliability index can be expressed in this particular form. Beta is equal to expected value of the performance function. As I said, performance function can be represented in various ways based on capacity and the discharge into stormwater drain, based on maximum velocity, minimum velocity. We can express different expressions for the W. Expected value of W divided by standard deviation of that performance function W is what is called beta. Now, why are we calling it as reliability index? Somebody said it is a reliability index. Can we take it as reliability index? Now, what is this on right hand side? Whatever we are seeing, we have expected value by standard deviation. If we look at it carefully, we appreciate that it is we can realize that it is nothing but inverse of coefficient of variation. What is coefficient of variation? It is standard deviation by mean. Instead of that, it is reciprocal of that or inverse of that. Now, we discuss the point that W should be greater than or equal to 0 for a system to be, or for a drain to be considered in success condition. W should be greater than or equal to 0 for a stormwater drain to be considered in a success condition. Whether you are picking up top formula or middle one or bottom, any of these formula, W should be greater than or equal to 0. Now, so this one, larger the value of what we find in the numerator, better it is. And what is standard deviation, the denominator part? The denominator part, what we are finding, that standard deviation, it just gives a scatter, right? Standard deviation gives information regarding how the values of W are all spread in the W axis, along the W axis. Now, this spread should be as less as possible if we are considering a system to be functioning properly. If the spread is more, it means sometimes you are getting negative values of W, sometimes you are getting positive values of W, and also the gap between them is quite large. That's what it indicates. Now, if the standard deviation is less and the expected value of W is fairly high, then beta value should be large. And that indicates obviously that the system or stormwater drain is reliable condition. So beta, considering that as reliability index, makes sense. Now, we can calculate it based on the probability density function. So here we have, right, the shaded area which is towards the left side is what is the reliability. This PS information what we are getting, the reliability is the probability, basically it is non-exceedance probability. What we have as reliability is non-exceedance probability, right? So one can get it based on this. So this is Gaussian distribution, and this phi is nothing but a cumulative distribution function of the Gaussian distribution. And the area towards the left side of that, the shade area gives us the reliability value, PS. In case if the value of beta is negative, so here this figure, it indicates beta value is positive and the corresponding value is what we are getting. But the other thing is beta can be on the left side also. Beta is on left side, what it indicates, it means expected value of W should be negative. The standard deviation can never be negative. This numerator should be negative, beta has to be negative. So it means that the system is entering into failure mode very often. So this one, if we see, if it is on the negative side, then we can make use of these equations to work out this PS value, the reliability value. We can calculate based on this formula, 1 minus phi, cumulative distribution function of the modulus of beta. That we can appreciate looking at this diagram. So basically we want the shaded area towards the left side of that. That shaded area is same as shade area towards the right side of this. Why? Because this is Gaussian distribution and it is symmetric about the vertical axis passing through its center. So the shaded area towards the left side will be equal to shaded area towards the right side. In order to get the shaded area towards the left side, what we do, we get this shaded area. If we take mirror image of the beta value towards the left side of it, the mirror image of the left side point will be onto the right side, and we are calculating what is the CDF of that. So this shaded area is what we are getting. That shaded area we have to subtract from 1, so that we get this blue color shaded area towards the right side, and that will be same as this blue color shaded area towards the left side. So this is how it works out. So based on the Gaussian distribution, one can get the estimates of their reliability. Using the standard normal tables, we can get it, or we can also make use of this Abramovich-Stevens formula to come up with that particular estimate. As you can see, this Z is nothing but the point that we are specifying on horizontal axis. So corresponding to Z, we can get W, and that W, if you put in the top formula, we can work out what is the P, exceedance probability. And once we know exceedance probability, we can work out what is towards left side, which is non-exceedance probability. Now, if we look at what we have discussed, we discussed the point that a stormwater drain is in success condition when the discharge is greater than the capacity is greater than discharge. If discharge is greater than capacity, then it is in failure mode. The first order variance estimation method is one of the useful procedures. Why I have put here is there are several random variables in this. Capacity of drain depends on several random variables, and typical examples of those are the channel dimensions, slope, roughness, etc. And if you look at the discharge entering into a stormwater drain, that depends on watershed characteristics, rainfall, etc. So we have M1 random variables which are influencing the capacity of a drain, and we have M2 random variables which are influencing the discharge which is entering into a stormwater drain. Now, whole together it is M1 plus M2, that many random variables are involved in this particular analysis. So if you are considering this, as we discussed earlier, the inverse of the CV kind of a term can represent the reliability index. So that is what we are trying to do. We need information on what is the mean value of W, what is standard deviation of that. So that is what we are trying to calculate using a different procedure. So what is that we are trying to do here? The design point is considered to be the expected value of W, right? So that one, the expected value of W, how we are calculating that? We are calculating that by considering mean values of all the random variables. We have so many random variables. Using the mean value of those random variables, whatever estimate we get for the performance function W, that is what is considered to be expected value of W. Then standard deviation of W is another thing that we need. So to proceed towards that, we are looking at Taylor series expansion of this W. So Taylor series expansion of this for single random variable I am showing. There are several random variables involved in the analysis. But if you look at single random variable, if we expand, look at Taylor series expansion of W, And if you're discarding the higher order terms, then we'll be left with the initial terms, and there the terms can be shuffled to get this. The f of x bar is nothing but expected value of w, and this second term we are seeing, this one. And if we just shuffle the terms here, we are getting it in this particular manner. Now the variance of a random variable can be expressed as expected value of that random variable minus expected value of that whole square. Now w minus expected value of w is already derived, so if you put that into this expression, we can solve and get this particular expression. So let us not focus too much on this. This is for a single random variable. Analogous to what we are seeing in the case of a single random variable, we try to extend it to multiple random variable cases. So once we look at multiple random variables, then the expression can be expanded in this particular form. Earlier equation what we saw, dou f by dou x whole square to standard deviation x square is single random variable x which is going in here, right? So here in the next one, what is happening? We are looking at several random variables, because there are several random variables influencing capacity of a stormwater drain, and also several random variables influencing the flow which is entering into stormwater drain. So everything put together we have this, but in addition we have this particular term. What is it taking care of? It is taking care of the covariance structure, because when we are looking at different set of random variables, there will be covariance structure across them. So that is what is taken care of. So now how to solve for this? So we can solve for that in this particular manner. What exactly are we trying to do? Each and every random variable I pick up, because this term is corresponding to each and every random variable. I increment the value of random variable by adding standard deviation. I calculate w. I deduct standard deviation of the value, and then I calculate the w, and then they divide by 2 times standard deviation. This is what we are doing, right? Incrementing and decrementing by standard deviation, and then working out the values of the performance function, and then we are calculating this. So this is what we got, and substituting that in this particular expression, we can calculate the value of standard deviation of w. So reliability index is the ratio of the expected value of w by standard deviation of w. So we can work out the value of beta. So that's what we can get. Now the reliability index is that, and excuse me, and the reliability is the area towards the left side of this, and that we can calculate using the Abramovich-Stevens formula or standard normal tables. Now, what are the shortcomings with this particular procedure that we looked at? Here again, the Gaussian distribution is what is assumed, right? So it's the form of distribution has skew. It cannot account for that. And also, if the functions are linear, what we are considering here, right? So it is ineffective in estimation of mean and variance, because those are only 2 terms that we are considering here. So it is ineffective in estimation of mean and variance for nonlinear function. That is another problem with this particular procedure. Now, this is basically the performance function. There is one other method called Rosenbluth point estimate method. I have been provided only 1.5 hours, so I'll skip through this because I'll get stuck up here. I'll just get started with this. So what we have done is there's something called as Monte Carlo simulation procedure. Mostly people are using means the limited studies, but people are using this. So what actually we do, I already defined this performance function W. So it depends on set of random variables, n number of random variables, some of those influencing capacity of a drain, some of those influencing the discharge entering into a drain. And these are the different performance functions that I have defined. Now, what exactly do we do? We can generate a large set of realizations for each of the random variables. There are n number of capital N number of random variables. We can generate lot of values for those random variables, and once we generate values for those random variables, those in turn can be used to calculate the W value, right? So to do that, what is that we need? We have to quantify the probabilistic characteristics of those random variables. What distribution are each and every one of those random variables following? So we have to make some assumption regarding that, and then we can start generating. If you are having, let us say 10 random variables, so from 10-dimensional space, I have to generate so many random variables, right? Several sets of such values can be generated, and using those generated values, we can calculate the value of W. So once we have the calculated value of W, they're called realizations. So 100 realization means 100 such values I'm generating. 100 each is like 100 rows and 10 columns. If you are dealing with 10 random variables, like 10 columns, and then 100 realization means 100 rows. We can think of like that. Using each row's information, we can determine the value of W. And once we determine the value of W, based on 100 values of W, we can determine what is the mean value of W. We can also estimate the standard deviation of W. Now, once we have the value of W, we know very well if the values of W is positive. The value of W is positive means what? The capacity is adequate to accommodate the discharge entering into that. We can visualize like that, or the other way around, using in terms of velocities. So we can see how many successful cases are there. If 100 realizations are there, out of 100 realizations, how many are in success condition? That I can count and put it in numerator. And n is the number of realizations that we are having. So this gives us a reliability value. Now, one can generate using the Abramovich-Stevian formula and all that. So that's what we can do. So we have proposed a procedure which is for use in fuzzy framework. So what is this procedure in fuzzy framework? We have extended the Monte Carlo procedure to fuzzy framework. How exactly we proceed, I'm going to talk about here. So performance function we have to define, and then memberships, the shape we have to assume. So here we have considered triangular membership shapes for the capacity of the stormwater drains, for discharge entering into stormwater drain. All of them, the triangular shape is what is assumed. Now the corresponding the membership for the performance function is also determined, and using these formulas. So how do we construct this? Basically, we know what is capacity, means in design condition what is capacity value we know, and that's plus or minus standard deviation we have to put, and in order to get this. So as I said, nobody maintains records of the capacity of a stormwater drain, because a lot of material keeps entering into that, so its width may be getting reduced, or again getting back to normal conditions. A lot of dynamic changes keeps taking place. So likewise, bed also could keep changing. Somewhere scoring can occur, somewhere deposition can occur. So we can assume some value for standard deviation, and then based on design capacity, whatever is there, that can be expected value of QC, and we can fix up these points on left hand side and right hand side. So we are assuming values for standard deviation, fixing up these values. Likewise for the discharge entering. So discharge based on our model, whatever values we get, based on that we can determine what is mean value of discharge and what are the standard deviations. So we can determine these points. So once we have these points, then we can define the membership function for the performance function. And the membership function, the left hand value, how do we get it? It is QC minus QD, isn't it? The QC1 minus, we would like to go as far as possible to left side. So we will not be deducting this one, but we will be deducting this one. So QC1 minus QD3 will provide us this value. And towards the right side of that, to get, we should do QC3 minus QD1. That's what we should get, to stretch as far as possible to the right side. And we define the shape of this. Now exactly what do? We have to generate number of values between 0 and 1, and that we call it as here as alpha cuts. So here you can see I'm defining a value here. I'm just cutting, right? A dotted line. I'm cutting these membership values. I'm getting corresponding values on. So for each cut, I'm getting 2 points on horizontal axis. Wherever it cuts the triangle, I'm dropping vertical. I'm getting 2 points on horizontal axis. So now what I do, I start generating values from this. Randomly I pick up values from this. Correspondingly I pick up values from this. So corresponding to every capacity value here, I'll have discharge entering into stormwater drain, a corresponding value there. And we know very well that the difference in this is what is going to, these values are called alpha cuts. So each alpha cut will give me 2 values here, 2 values there, and that is what I am denoting by this. And once I have these values, then it is obvious that the difference in them, the QC minus QD, is going to give me W. Now, this W is what is defined. So how many alpha cuts I am considering? I define a range. I define this thing for that. So how many alpha cut intervals I consider? We can change that number. So we performed experiments with n alpha number of alpha cuts. Then I said for each and every alpha cut, I get two values on horizontal axis. So I have a bound here. I also have a bound here. I can pick up one value from here, one value from there. So several such sets of values I can pick up. So I defined NSIM as the number of values for that, because it's the Monte Carlo simulation method, and each simulation involves picking one value from this range, one value from that range, and we calculate the W values accordingly. So we got total NSIM values of W. So with that, we can calculate what is the mean and standard deviation. And we can also do one more thing, that is now that we have this function, the W, we can determine above the alpha cut what is the area beneath that function, and towards the right side of a threshold that we specify how much area is coming. Why do we do that? Let us say, strictly speaking, the W value should be positive, means it should be towards right side of this thing, and we allow value called tolerance limit. What is that tolerance limit? Just like the geotechnical engineering, we talk about surcharge and all that. When the water is entering into a stormwater drain, the water can accommodate some water which is in excess to its capacity slightly. So, but it will not be flooding the surrounding area. So we can allow small tolerance limit on top of it. That is also allowed. And then we calculate this particular part. So here you can see that the area which is towards the right side of this tolerance value is what we are seeing. So this is in success condition, and here it is entirely towards left side, means it's for failure mode. And if you look at this one, the tolerance value is coming here. Partly it is towards the right, partly it is towards the left. So this hash part divided by the total area is going to provide us the fuzzy reliability. So this is what we work out. So now for each alpha cut, I'll get fuzzy reliability value, and we can assign weights to fuzzy reliability estimates obtained using different alpha cuts by this expression, and we can solve this to get the reliability for the conduit. So this is the fuzzy procedure that we have proposed. And now the main issue is what I was mentioning. We have stormwater drain networks, and stormwater drain network, if we quantifies the performance of individual drains through some metric, that will not be adequate, because there will be several drains in each and every chosen network. So can we say that this sub-branch of a network is in needs more attention compared to sub-branch of some other network? So to proceed towards that, we have come up with a procedure, and this is based on reliability block diagrams. And here you can see that a network is constructed which is analogous to the network of resistors and all that. No, in the physics, the 10th, 11th standard and all that people look at, right? Network of resistors and all that. So analogous to that, we can construct a reliability block diagram for stormwater drains. So here these drains 1, 2, 3 are all in parallel, and they are in series with this. So now the question which arises is, okay, we are preparing reliability block diagram. Will it exactly resemble real world network? The answer for that is it won't exactly resemble the topology, but it has mostly some resemblance. Not exactly, but it has some resemblance. Then how to construct these ones? How to decide whether the drains are in parallel or in series? So for that, we have come up with some set of rules. So through this example I talk about, so this is a hypothetical stormwater network that we have picked up for this analysis to begin with. So you can see that this drain AB, this drain, it receives this node A. At node A, it receives from both subcatchments A and B. And at node B, it receives from the subcatchments 5. So total we have 13 subcatchments in this. The drain AB drain CB and drain DB, all three drains, the flow in them are unaffected. Means one is not influencing flow in other one. Right? Flow, the drain number 1, drain number 2, drain number 3, flow in one drain is not affecting flow in other drain. So we can consider them to be in series, the parallel. Why they are in parallel? Because flow in one drain is not affecting the other one. Now the flow in drain 4, it depends on flow in these three drains, 1, 2 and 3. So we are connecting them in series. So like this we construct. So this network we picked up and then we performed analysis based on the fuzzy method that I have discussed. Now, I said we have to come up with some kind of a measure, performance measure for the entire network. How do you do that? Just like in the case of the resistors, etc. Here, when the drains are in series, then the reliability of those drains, once we take product of them, then it results in the resultant reliability for the network, for those which are in series. When they are in parallel, this is the formula that is proposed. So now, if we look at this particular network, one can implement these equations and come up with equivalent reliability values for those which are in parallel. Then considering them to be in series with other, we can come up with, for the whole network, we can come up with the reliability values. So what we got as an end result is that based on the fuzzy Monte Carlo simulation experiments, when we come up with the reliability estimates, the reliability estimates are in general higher than what we get with the conventional method. And if we are trying to use this procedure is not only for coming up with some estimate of that, we can also use the procedure for retrofitting the stormwater drains. Earlier I said we are considering parameters like number of alpha cuts and number of simulations, the number of values I'm picking from the ranges for the capacity and the discharge entry into stormwater drain. So the effect of all that we have studied, and generally the values are not so sensitive. That's what it has indicated. So in general, if we pick up number of alpha cuts as around 50 or the number of simulations around 500, etc., it should be fine. Now, this procedure can be implemented for designing a network. How this can be done? For example, we have this network. Now, what I said is this whole thing is in series with these other three. So using the formula, this earlier I said they are in series, we can take product of the reliability values to come up with the system reliability. We can use that to come up with the reliability value for the entire thing. So we want to design a network so that the reliability of that is 99.99. So we can look at this and we can come up with the individual reliability values. Now, once we have individual reliability, now reliability of each one of them and the reliability of this, there should be 0.997. So considering that as the beginning point, now if you proceed to this one, this top one is in parallel with this and this. So if we consider that, we can come up with the reliability value for the top one, right? So once I pick up this one, this whole thing is in series with this and this. So we can come up with the reliability value for this 1, 2, 3 put together, and that is working out to be this one. Then we proceed to this particular part, the part 1, 2, 3 put together. Reliability value should be 0.949. So for parallel, we have given this formula. So implementing that, once we work out, we can get the reliability value for individual drains. So if a reliability value for a drain is specified, then we can come up with the dimensions of the drain for retrofitting, etc. So that we have implemented on real-world system in Bangalore. That is what I'm showing here. So total we have 19 links in this particular network. There are series of tanks, etc. And we have implemented this on that. So this is the reliability block diagram constructed for the real-world network. And we came up with the dimensions. So these are the existing dimensions. So for retrofitting, for example, here you can see depth, slight increase in depth and slight increase in width. So various things are being considered. Compared to conventional method, Monte Carlo simulation, fuzzy Monte Carlo simulation is providing values on economical side. Means these dimensions are on little lower side, and we can achieve the desired reliability. So those values are what are shown here. Now we are looking at the land use land cover change impact and all that. A lot of change has taken place in the land use land cover pattern for the Bangalore over the past several years. So several imageries we have picked up, and we are modeling the land use land cover and seeing the possible near future scenarios. We cannot go into too far into future because at this rate, if it is changing, then we can speculate only for near future period. And we are accounting for that to see what kind of changes we can expect in flow in stormwater drains. The climate change impact assessment, of course, we are looking at regional climate model. The development is also taking place at ISC. So we are coming up with the possible change in scenarios for rainfall and other climate variables, etc. The type of scenarios for that, and they are being fed into the stormwater management model to come up with the possible flows corresponding to different climate change scenarios. So as you know very well, the global climate models provide the end conditions to run these regional climate models, and the resolution of this is also quite large. So we try to downscale and get the information for use at watershed scale. There are some interesting things that we can think of. One is there are locations having karst deposits abroad, and all people are focusing on that. So they can have some implications on the type of networks that we plan to have. Because in karst areas, etc., if we are having, so you can, this map is showing different locations where we have the karst deposits, carbonaceous deposits, etc., and the hydrogeologic formations are of typical nature in those areas. So we should have some special linings and protection works where the groundwater is located at a relatively shallow depths. So one can design these linings, etc. Next is the forecasting systems. So these recently also in Bangalore, we are looking at proper forecasting systems. As I said, there are two types of problems that can be taken up over urban stormwater networks. One is forecasting what is going to happen few days from now, etc. And for design and risk assessment, performance assessment, one has to look at long term. That is what was the focus of my talk. But from a forecasting point of view also, one can look at it in order to come up with some appropriate preparedness measures to mitigate the likely damages from the floods. And in that connection, we have set up in Bangalore, over 100 gauges have been set up by the KSNDMC or local organization. And focus should be there on developing better hydrological models. As I said, there is lack of knowledge, so more input should go into gaining proper understanding of the system, and all systems are not alike. So one has to come up with models which can take into account these hydrological aspects and also the meteorological aspects. There is a rapid change in land use land cover. There is a feedback between land use land cover change and also climate. It's not individually, separately modeling climate change effect and the land use land cover change effect. The combined land use land cover and the climate both have interactions, and their combined effect, what can be the flow effect of that on the likely flows into stormwater drains in the future. One can look into that direction also. And these days the socio-hydrologic aspects are gaining more attention, so one has to have socio component in the modeling whatever we are looking at, and sustainable mitigation strategies have to be developed. One typical example is in Kuala Lumpur. We can see one can try to effectively utilize the stormwater networks for various other purposes also. There's a typical example where the motorway and the stormwater tunnels both are used. It serves both purposes, stormwater conveyance as well as the pathway for the motor vehicles. It is an interesting thing, and they monitor the network and all that. Another thing is these days there's more attention towards the smart cities. So everything, including the stormwater drains, are designed in such a way that most of the water, it infiltrates in that locality only, so that we have scope for recycling the water and using it locally. And also there's emphasis on the rainwater harvesting. Recently, a product has come up in Bangalore. As I was telling, we have good network of rain gauges. Of course, the data are there available for only recent period, about 6 years or so. And for forecasting, model is developed, and an app is developed, which is called Mega Sandesha app or Vanura Mitra app. So it is between through collaborative efforts between KSNDMC, which is local organization of Karnataka, and ISC, and it provides alerts on the weather and the rainfall, flooding, so that people can safely move from one locality to other locality in the urban setup. Thank you. And if there are any questions, I can take.
Thank you, sir. Sir, we have one question from the participant, sir.
Yeah,
how
please.
to derive Manning's roughness constant for flood modeling studies?
Manning's roughness constants, a lot of studies have been carried out abroad, and based on the nature of the surface and all that, using tables, we can readily use the formula. Or in laboratory also, we can carry out experiments by creating artificial sand grain roughness and all that. We can perform the experiments to see what can be implications of that. So way back in 1970s, 80s itself, Professor Cho, when he was alive, very nice set of values he has provided, and several studies, even USGS also, there are several reports where they have carried out studies to indicate what kind of Manning's roughness factors one can take for use in different situations.
Sir, we consider percentage of permeability of paved and unpaved surfaces of the catchment during stormwater modeling. Should we consider?
Yeah, that is needed, because otherwise we are making some kind of approximation.
Professor Srinivas, this is Praveen.
Hello.
Professor Srinivas, can we use the Manning's roughness, which are actually derived for freshwater? Because could it be dependent on viscosity and other things? Because most of the times you have combined sewages and stormwaters. So how far
Right.
the density and other aspects would affect the Manning's roughness?
Yeah, actually, yeah, you are right in the sense that for exact conditions which are prevailing in the field, there are no values available. Any type of values that we get from the standard textbooks, they are from a specific situation. But for whatever situation we encounter in the field, there won't be any values available. And generally, once we have more roughness, then the Manning's roughness value goes up. And how much and where, and can we assume same value for the entire network? That is also a question mark, because several locations, the type of resistance the water encounters are different, and also the type of water can also change from one branch of network to other branch of network. It depends on what kind of water is being discharged into that. So the more the roughness, the higher will be the value. Is obvious, but nobody can say this is the value that one should take. In my presentation itself, I have shown how the conditions of stormwater drain are. So specifying one value for that drain, it is really a challenging issue. One of the uncertainties among so many uncertainties that I have addressed in my talk.
Sir, one more question is there any analysis, a quality analysis regarding to Bangalore city, whatever the case study that you have taken up, is the quality is also assessed at some point so that the monitoring can be done?
There's a different group from ecological sciences of our institute who are focusing on the quality related aspects. I am dealing only with quantity. Quality aspects are very much important.
So next question. Sir, what is the criteria in selecting the percentage of permeability? How much should we select?
No, we should look at the land use land core pattern, and then based on that, you cannot assume some gross value for that and proceed. If the method itself is of that kind, then if you are specifying only some percentage, that means that method itself is some lumped kind of approach we are using. So each and every subcatchment, we have to see what is the type of land use land core pattern which is prevailing, and then we have to incorporate that in the modeling.
I request the participant to raise a question by unmute yourself.
If there are no further questions, one more I would like to know, sir. Is there any place that it's been retrofitted and then it's functioning well, or is there some kind of assurance or reliability on that some Indian city where it's retrofitted for the present scenario and then it's functioning well? Is there any such case?
Yeah, I cannot see. I have no idea about other cities, but as far as our city is concerned, very recently at several locations the drains are retrofitted, and they are functioning well. Not everywhere, but wherever they have retrofitted, in my surrounding itself they are retrofitted and they are functioning well. In fact, it is just adjoining our ISRO. We have ISRO headquarters here. Just adjoining that, it is doing well. And it was subjected to flood when I was residing there. Heavy flooding. After that, only they have retrofitted, and till now it is functioning well.
That's really a good news, because probably that's the only option that's left to our subcontinent, that we need to retrofit these things. Yeah.
But the issue is, the stormwater drain network itself is quite large in the city. It runs into hundreds of kilometers, and the thing is, we are covering right now. We are doing a project, and hopefully by the end of it, we'll have complete idea regarding what is happening in which corner. Recently itself, there has been flood in some part of Bangalore, including just like Hyderabad washing away of cars and all that. So situation is not same everywhere. That is obvious. And hopefully the interaction between the state government agencies and the education institutes, that is very much essential. We have taken up initiative in that connection, and then we hope we are proceeding in the right direction. Still the fruits are yet to be reaped.
Sir, one more question, sir. Is soil test is required in contest with the soil characteristics?
Yeah, certainly they are necessary. They are very much necessary, and they are highly, their characteristics change quite a bit. Inhomogeneity, anisotropy, so there changes, right? The characteristics change quite a bit. So it is not within my domain. It is a geotechnical engineers who have better idea of that. But the soil characteristics, once we make some kind of gross approximations, then though we do other things properly, here if we do some kind of error, then the implications will be obvious in the end results.
Shivaparvati, if there are no more questions, can we? Are there any more participants who would like to ask questions? Please find out. And if there are no more questions, then we can move on to valedictory function.
Incidentally, I wish to mention one more point also. See, the frequency analysis of rainfall is a must in this kind of studies. And one point that I did not touch upon is that we have different causal factors for rainfall. Assuming that whatever rainfall we get is entirely homogeneous, that does not make any sense. For example, even if you look at our own Andhra part, We have the cyclone caused rainfall. We also have rainfall arising due to northeast monsoon, southwest monsoon, the local convective factors. So we cannot apply simply some distribution, fit it and get it. Something else it provides. So one has to look at it from this angle, and some kind of mixed distributions are what are desirable in our part of the country. So that's what I recommended even for our Amravati city when we are looking at that.
Sir, one more question, sir. How will you validate the reliability model in this analysis, sir? What is the validation procedure will follow, sir?
Yeah, so this requires I think a validation for reliability. The thing is, first of all, our stormwater management model has to be validated. And as I mentioned, there are no data available at many locations. The gauges are being set up as far as Bangalore is concerned. Very recently, that initiative is taken. So whatever model we develop for a given amount of rainfall, if you are getting some amount of outflow, how far are we sure that that is a reliable flow into a stormwater drain? To assess that itself, there are no gauges. So if the gauges are there, then one can assess that, then one can validate it. Whatever parameters we are calibrating, those calibrated parameters, are they effective or not, we can consider it for validation. Of course, for validation also, there are different procedures. Bit sample validation, k-fold cross validation, variety of techniques are there. But the main important thing is there are not many locations where we have the gauges set up in stormwater drains to take the readings of how much flow is passing through that. May not be entire year long, but at least during the flood events.
Yes, sir.
So that direction, there the validation should be done properly. Then the question comes is, we apply different type of reliability procedures. As I said, I discussed a couple of procedures. One can try different options there and then talk about the uncertainty in reliability estimates. I am trying, let us say, 4 different procedures. How are my estimates going to be different from one to another? If the estimate I get for reliability is quite different based on one method compared to other method, then the question arises is that method going wrong somewhere, or that kind of a thing. So reliability analysis is what deserves more attention, and of course the uncertainty analysis is what deserves attention. And reliability is not the only thing. As I said, vulnerability, the resilience. So one has to look at a combined view, and then they can try to rank these networks. For example, as I said, if grants are there, they are limited, and government has to take a decision on where to invest. That is where we can chip in and provide them. This is what we looked at, and possibly we can take initiative in that direction.
Hello, sir.
Yeah, please.
Sir, good evening, sir. Myself, Chandramouli from MVZ Engineering College, sir, Vizianagaram.
Hello.
Sir, actually, I have a question. The reliability of the stormwater drain, sir, is it time dependent, sir?
Reliability, whether it is time dependent? No. The thing is, when we are doing this analysis, what we are considering is critical storm events. So those which have occurred in the past, they can be used, but they are not the basis to declare the system is reliable or not. So we are constructing so-called synthetic storm events, and based on those synthetic storm events, we are evaluating whether system's performance is acceptable or not. Means in what range the indicator value is changing. So, yes, so we cannot say today it is reliable, tomorrow it is not reliable. That we cannot say that way. Of course, one more point I mentioned is under climate change scenario, land use land cover scenario, also we are seeing that. So whatever estimates that we get for climate change scenario, land use land cover scenario, those estimates for the reliability are likely to be different from those which we are getting by assuming that stationarity prevails.
Yes, sir. Sir, one more thing is sir, the age of the drain, with respect to age, its performance deteriorates, na, sir. So its reliability comes down.
You are right. You are right. And these days, more attention on that is being given in the dam rehabilitation improvement program, DRIP program of the central government. The dams and all that, because of the weakening of the material due to aging and all that, the breach can occur. And of course, here also those things are applicable, but we are looking at much smaller scale structures, the size and all that. But the implications will not be as substantial as what we find in the case of dam breach. The material age is definitely an important factor. Of course, there we look at material age of dam, we look at earthquake loading, we also look at hydraulic loading, and different is a compound risk analysis. That is what is desirable. So here, if some studies are carried out with regard to, I said, the minimum velocity, maximum velocity, based on that also we can define performance of a network. So if based on age of that, how much velocity can be allowed in the stormwater drain at that location. If some studies are taken up, they can come up with values for that, which can be used in the analysis.
Yes, sir. Thank you. Thank you so much, sir.
Thank you.
Any other questions? Sir, if you don't have any questions, we can close the session with our valedictory session, sir. I welcome all the, good evening. I welcome all the participants for the valedictory session of the 3-day online workshop on urban stormwater management, which is being organized by the Department of Civil Engineering, Andhra University College of Engineering, Visakhapatnam. This workshop is being sponsored by TechU Phase 3 Fund, sir. I would like to take the pleasure of inviting our beloved head of the department, Professor T.V. Praveen Garu, and today's guest of honor, Professor V.V. Srinivas Garu from IISc Bangalore. Sir, welcome you all. Welcome you for the valedictory section of the workshop. So now I request the head of the department, Professor T.V. Praveen Garu, to speak a few words about the workshop.
We are really lucky to have very knowledgeable and who have acquired a great degree of expertise in stormwater management, people, resource persons who have been experienced in this field, giving us an opportunity to associate with us in the form of giving lectures, especially Professor Govindraju sir, in spite of having his schedules simultaneously in US, because probably his sleep time has been considerably reduced because of his working late nights because of the time lag between India and US, and then still the time otherwise he would have taken rest he spent for us. So I should really thank him for that, for his kind of the passion and then the kind of enthusiasm he has shown in organizing this workshop, contributing for this workshop. I'm really grateful for him. I'm also grateful for all the resource persons, Professor Srinivas and Professor Nagesh and other people. I also, I think I suggest Dr. Shivaparvati to give away certificates to to those people who are helping you in coordinating this workshop, which probably you are not planning so far, but I suddenly recollect that it's better we encourage students' involvement in organizing this workshop. So whoever is organized, I think you should give away the certificates for associating themselves in organizing the workshop. Department of Civil Engineering, we actively conduct this workshop. In last 8 months, we have at least 6 or 7 such workshops. Every couple of months, in every 2 months, at least one workshop we are conducting. We conducted Indian Geotechnical Conference last December. So we have been quite active in that, and with all the support from faculty from other bigger, better universities, we are able to do this. Universities or institutions, we are able to do this. So Thank you so much, Sivarati, for conducting this workshop, and also thank the resource person.
Thank you, sir. Now it's my privilege to invite our guest of honor, Professor V.V. Srinivas Garu, to deliver his valedictory address.
Okay. Good evening to you all, and I thank Professor Praveen and Professor Shivaparthi and Andhra University for giving me an opportunity to deliver a talk on this occasion. And it has been a pleasure to participate in this. Of course, I very much believe that this kind of lectures are initial. They're the kind of initiatives that help a larger group of people to learn certain aspects, and of course the discussion that takes place after that, it triggers some kind of thought process which will eventually help many of them to pursue research in certain areas where they may be having some kind of interest but might not have started the work because of lack of proper understanding. And of course they also have to maintain some kind of contact with the resource people. It's not that whatever we are interacting, that's the only session which is meant for interaction. They can communicate with the resource persons for a long run, and I believe that the dialogue exchange and exchanging views in a long run will be helpful for both parties, and that is what is essential in doing some meaningful research in whichever area we are looking at. I once again thank the organizers for this good initiative, and I hope it's a continuous process. At IISc we had actually several years. Every year we used to have something called as monsoon school. Every year during June time, wherein participants from entire country and even abroad, they used to come and participate in the program. And this kind of exchange of views is very much essential for proceeding in right direction. I thank you all once again, and thank you so much.
Thank you so much, sir. I request the participants you can give your feedback regarding the workshop. You can unmute yourself and give the feedback.
Yeah, madam, good evening, madam. Myself Chandramouli from hello.
Yes, sir.
MBZ Engineering College.
Yes, sir. We could able to hear you.
First of all, I congratulate the Department of Civil Engineering, madam, for conducting such a wonderful workshop. And what I felt that all the resource persons are they are very good, madam. So and also the topic is also very apt, because nowadays we are facing so many issues related to urban stormwater management, and really they have provided the very good content. The content is also very good, and also all the resource persons are highly knowledgeable in this area, and definitely the participants they are very much benefited by this. And personally I congratulate you, madam, because you have taken all the trouble in order to organize this particular workshop, and thank you so much for your invitation for me to attend this workshop. Thank you so much, madam.
Thank you, sir. Any other participant want to share the feedback? Actually, in the chat box, I was getting a lot of comments that everyone is happy for attending this workshop. So I hope that all the technical sessions of the workshop are interesting and helped you to gain ample of technical knowledge in the topics of presentations. So first of all, I would like to thank all the participants who have taken the interest in attending the 3-day online workshop on urban stormwater management and making it a grand success. My sincere and humble thanks to all the resource persons of the workshop, Professor Rao Govindaraju, professor at Purdue University and also a visiting professor in the Department of Civil Engineering, Andhra University, Professor Nagesh Kumar from IISc Bangalore, Professor V.V. Srinivas from IISc Bangalore, Professor N. Uma Mahesh from NIT Warangal, Professor Wazir Muhammad from Andhra University, who have accepted our invitation with short notice and delivered such a knowledgeable information to all the participants in due course of time. It's my privilege to thank our Vice Chancellor, Professor PVZD Prasad Reddy Garu, for providing online platform to conduct the workshop during the COVID-19 pandemic situation. It's my honor to thank Professor Peri Srinivas Garu, Principal, Andhra University College of Engineering, for supporting this workshop with the financial assistance from TechU Phase 3. With due respect, I thank our head of the department, Professor TV Praveen Garu, who has given me the motivation and encouragement for making this workshop successful. Now it's time to thank my fellow faculty members who have guided me in every stage of the program with their kind, encouraging words and suggestions. I would like to thank my research students and the technical team of the Computer Center for their assistance throughout the program. Last but not the least, I would like to thank the press and media for their wide coverage of the workshop. Thank you, one and all. All the registered and attended participants will receive their certificates within 10 days. Once again, thank you to one and all.
Professor Srinivas, shall we close this?
Yeah, thank you.
Shall we close this?
Yes.
Thank you so much,
Thank you.
Srinivas.
Yes.
Yeah.
Thank you, sir. All the participants, please fill the feedback form and submit.
Okay, bye, Srinivas. Bye, sir.
Bye. Bye.
Thank you, sir.
Thank you. Thank you. Bye.
Yes, sir.